What's up, everybody? Welcome back. In the last video, we sort of went over some uh, like sort of stuff that we maybe need to go over in more detail in later videos, but like functions and uh, preprocessor directives and things like that, or precompiler directives rather. Sorry, but before we do all that, I think we really need to just sort of start with variables and types, variable types, because those are sort of the basic things for programming. Um, because what they are is the most basic way to store data, and obviously, when we're programming, a lot of what we're doing is data manipulation. Um, you know, arguably everything we're doing is data manipulation. So, storing data can be very useful and is sort of the building block and foundation of all programming. And if you don't know about variables, you can't really do anything. So, with that in mind, I'm going to start by talking about variables. We're all probably familiar with sort of basic variables if you've done like algebra, right? You've seen like 5x equals 10, then you divide both sides by 5, and you're left with x equals 2, right? And x is the variable, right? And in algebra and stuff, it's like the idea is to find the variable, solve for the variable. That's a little, I mean, it's essentially the same thing what a variable is, but it's a different concept in programming. We're not really generally trying to find a variable. We're assigning the variables. We're telling the computer what the variables are, so we're not interested in finding what they are, but it's the same thing. Except we also don't, like, x is not a good variable name because it's not very descriptive. In math, they like to use x and y's and things like that, um, mostly for graphing purposes. But in programming, we want to use descriptive variable names because remember, the variable name doesn't really matter, right? All that matters is that it doesn't matter that this is called x, it just matters that this is representing 2. So if we were to write, for example, 5 cow, right, that's cow, equals 10, then dividing by 5 would still tell us that cow equals 2, right? And in this case, we can kind of see like maybe there's a point to this. Like maybe cow equaling 2 means that we have 2 cows or something like that. So it's sort of like a word problem type thing. And programming is a lot like a word problem because generally it's some real world scenario that we're trying to solve a problem, right? So, like, for example, um, well, before I get into examples, let me like write the code for assigning a variable. Because when we want to make variables, the first thing we have to do, step one, is we have to see if I can write step one. Step one, steel underpants. No, step one is declare. Declare. I do declare. And I'll even put these so we know it's a comment, right? And so if I say int cow semicolon, always a semicolon, right? Because this is a statement. If I say int cow and this int pops up again, we saw that in the last video and I kind of brushed it off in that video, and I'm going to brush it off for a second in this video as well, although I will cover, because int is the type. Cow is a variable of type int, and I'm going to do types. But what we've done is we've declared this cow. So what does that mean? Like, let's sort of ignore this stuff over here. But I'm going to draw a box over here. Now this box is a spot in memory. And in this sort of box, we're going to store some value of type int, and we're going to put a label on it, cow. And that's what the computer is basically doing. Obviously, it's not using an actual physical box, but it is sort of taking a spot of memory, labeling it cow, and saying whenever you use cow, I'm going to use, whenever you say cow, I'm going to use what's in this cow box to represent like as cow, which is what a variable does, right? A variable is some sort of thing, whether it's x equals 2, like x is representing 2, but we're not writing 2 explicitly, right? But it means 2. And cow will mean whatever is in here. And whatever is in here might vary, right? So our variable will vary based on what's in this box. And it's going to be something of type int. It has to be an int, which stands for integer. So 2 is an integer. Any number that's a whole number is an integer, right? Now, right now, there's nothing in this box, and that could cause us problems if we try to use the cow. But we'll, because we'll try to use cow and there will be an empty box. And that can cause problems for us later, but for now, we're just going to go straight into step 2 so that we don't have problems. We're going to assign. So we can say cow equals 2. And a semicolon. That's not an I, that's a semicolon. And this equal sign is called the assignment operator. And that's very important because we can sometimes, like this is kind of an equality statement. Well, I crossed it out maybe prematurely. When I have 5x equals 10, I'm using this equal sign as an equality statement. I'm saying that 5 times x is equal to 10, right? But I'm not assigning the value of 10 to 5 times x, right? So that's going to become interesting or important later on when we start evaluating things. But for now, we're not evaluating anything. We're assigning 2 to cow. We're telling the computer, put a 2 in the box. What's in the box? It's a 2. And we can actually do both of these steps in the same step, right? We can just say int cow equals 2 semicolon, and it's going to take both these steps in one, which if we know what we want to make cow right away is not a bad idea to do, because then we know for sure that something's in the box and we avoid that problem of an empty box that I sort of hinted at could be something that could be a problem. But then we're going to use the cow, and you might say, well, what's the point? Like, why don't we just use 2 if we're just assigning cow to be 2? Well, maybe we have some function, right? And we already kind of talked about functions. We haven't written any of our own, but we've used like printf, right, before, which is in the standard I/O. So let's say that we had some other library of functions like, buying bales of hay, right, which takes some number, right, 10, semicolon, right, and we're saying, and when we call this function, it buys however many bales of hay we tell it to buy, right? So since we have 2 cows, and I'm just using 10 because I already kind of started with this example up here, right? Let's say that each cow needs 5 bales of hay to eat, right? So when we want to know how many bales of hay we need to buy 5 times 2, because we need 5 bales for each cow, 5 times 2. But what happens if we buy another cow, right? Now we need 15 bales of hay because we need 5 bales for each cow, and now we have 3 cows, right? Now we don't have 2, now we have 3. So we would have to go back, if this was in our code, right, to every, so often we're going to call this function. This is a fairly contrived example, but, well, maybe not necessarily. But there would be a lot of other code going on as well, right? Like this line of code by itself would not. But anyway, if we were going to call this function every so often, right, this is no longer valid, this 10, because now we need 15, because now we have 3 cows. So now we need to go back in and change this code and recompile it before we can run it. But if we didn't write this, right, if instead we wrote bales cow times, this is the multiplication operator in C and most other programming languages, times 5, right, semicolon, then it's just going to take whatever's in the cow box. So when cow was 2, then it would buy 10. It would go 2 times 5, and it would pass that 10 to our bales, and it would be good. It would be like this. But then when we changed cow to 3, cow it's still doing this, So now it's cow times 5, which is 15, because now cow is 3. So we don't have to change, we don't have to go back and change the number that we're passing in here and recompile and do all that, because this is always going to be right no matter how many cows we buy or sell or whatever, as long as cows gets updated. So that's why variables, that's one use case for variables, of fairly useful, fairly simple example, I suppose. Um, but now I have to do types, and hopefully I can do types in a reasonable amount of time. It's kind of a complex subject, and for some reason I keep getting lines when I try to do things like that. But anyway, the C has a few different types. Has int, short, long, float, double, and char. And we've seen int. I've just sort of used it a few times and not really explained it. And what it is it's short for integer, and it means whole number, right? It's a whole number. So if something's of type int, it's a whole number. And why that's important is, if you remember our box that I drew earlier, right? Say we have 5 in our box, our cow box. We have 5 cows, right? 5 is not a symbol that the computer actually knows about, right? Like if you remember when we were talking about compilers, I was talking about having to convert everything to ones and zeros. So in this box is not actually this symbol, this 5, right? In this box is actually something the computer can recognize, which in this case is 101 and then a bunch of zeros preceding it, but those aren't really as important. And what this is this is a binary representation of the value 5. And in order to kind of understand that, I have to do a brief description of how binary works, and I think I can do that fairly quickly. It might not be the most robust explanation, but it'll be good enough for our purposes for now. So let's first think about decimals, how we do decimals. Deci means 10, it's Latin, right? And when you think about the Arabic numeral system that we use, we have 10 symbols. That's a 4. We have 0 through 9, right? Which is obviously 1 through 9 is 9, and then adding 0 makes it 10. So deca for 10, and we have 10 symbols. But then what happens when we add 1 to 9, right? Well, we don't have a symbol to represent 10, right? We don't have a symbol to represent 10. So what we end up doing is we use places. We use the concept of places. So we commonly write 10 like this, and everybody sort of just knows that that's 10. But what it really is we're using 2 columns here. We're using a ones column and we're using a tens column, right? So what this is saying is we have 1 10 and 0 1s. So we have 10 plus 0 is 10. And then if we add 1 to that, then we have 11, right? Then the 1 in the tens column and the 1 in the ones column is saying we have 10 plus 1, right? We have 1 10 and we have 1 1, which is 10 plus 1 is 11. And we can do that all the way down to 99, right? With the 9 in the tens column and a 9 in the ones column. So what this is saying is we have 9 tens, and 9 tens is 90, right? And then we also have 9 ones, and 9 ones is obviously just 9. But if we add 90, 9 tens, and 9 ones, then we end up with 99, which is the number we're trying to represent. But then obviously if we add 1 to this, we run out of symbols again, so then we have to make a hundreds column, right? A hundreds column. So I'm not going to draw it all out because it doesn't matter. You should hopefully be following what I'm getting at, right? So we have a 1 in the hundreds, a 0 in the tens, and a 0 in the ones, which is 100. Well, binary is the same way, except binary only has two symbols. We only have a 0 and a 1. So if we're trying to represent 2, we're already out of symbols to use, so we have to start our columns at 2. So we have a 2's column. So we have a 1 and a 0 is a 2, because we're saying we have a 1 in the 2's column and a 0 in the 1's column. So just like 1 0 represents 10 in decimal, because we're representing 110 plus 0 ones, 1 0 in binary represents 2, because we're representing 1 2 and 0 ones, right? And then 11, what would be 11 in decimal is 3 in binary, because it's 2 plus 1. And then again, we're out of symbols already. So just to represent 4, we already have to go to a third column and make a 4's column. 4. So we have a 1 in the 4's column, a 0 in the 2's column, and a 0 in the 1's column. If we add 1 to this, we have 1 0 1, which is the 5 from earlier, right? This 1 0 1 that I wrote up here represents 5, because it represents a 4 plus 0 2's plus 1. So it's 4 plus 0 plus 1 is 5. And then all these zeros that precede it here, those are there because this box, right, is not a literal box, but it is a place in memory. And the place in memory has things called bits. And each bit can hold either a 1 or a 0, right? A 1 or a 0. So each bit is like a column. So for the integer on my computer, on most modern computers, the box contains 32 bits, which could also be thought of as 32 columns. So to represent a 5, we've got, 30 zeros and then a 1 0 1, right? And these don't matter, just like if I wrote 4 with a bunch of zeros like this, right? Like none of these, this value is still 4, right? No matter how many zeros precede it, if I'm writing decimals, right? So this 1 0 1 is still 5 no matter how many zeros precede it. But this concept of the number of bits that we have is interesting because it brings us to shorts and longs. Because a short is a short interval, integer, sorry, and a long, as you might have guessed, is a long integer. And what they're talking about when they're talking about short and long integers is they're talking about the number of bits in the box that we have, right? So in the case of the short integer, instead of having 32 zeros or 32 bits, 32 columns in our box, we only have, in most modern computers, we only have 16 columns in our box. Now the reason that you might want to use a short instead of an int is if you're really concerned about memory space, right? Because these columns, these bits represent real spots in memory that we have to allocate to that variable, right? So the more that we do, like the less memory we have left for other stuff. So if we're low on memory, we might want to use shorts for things. Nowadays, people don't generally worry too much about using memory for specific things. For specific variables, we're not super worried about it, but it used to be a concern. And the downfall of a short is because you only have 16 columns, you can only represent, however many things can be represented by this, which it turns out to be about 32,768. And if you go over that, screwy stuff starts happening, and that can be a problem if you're using, 32,000 is a big number, but it's not that big, right? Like if you're writing bank software and someone has a retirement account with more than 32,000 in it, which you would hope that someone who's retiring would have, something screwy could happen where it wraps back around and becomes negative, and that's an angry customer, right? So you don't want to use shorts if you might think that your numbers are going to be bigger. Uh, and the same thing with longs. Longs these days are kind of uh, not really that useful, because most you would think that a long would be like a short is half the size of an int, so wouldn't a long be twice as long? Well, no, it turns out that most of the time longs these days are uh, are the same as ints, and the difference is mostly historical. So ints are fine. I'm going to be using ints for all my integer needs in most of this tutorial, I believe. However, this video is getting kind of long, and I haven't even gone over the other types. Right? We still got, scrolling down previously, we've still got all of these. So what do these do? Well, one thing you might have noticed is that integers are whole numbers. So what if I had like half? What if I had 0. 0.5? You can't have 0. 0.5 cows, right? But maybe you have some int gallons that you want to set to 0. 0.5. Well, that won't work because there's no concept of fractions in integers. So you have to use a different type, because the way that integers are stored is whole numbers, and there's no decimals in binary, right? It's only ones and zeros. So to represent uh, decimals, I'm not going to go into the actual way to do it, because it's even more complicated than this, right? It has to do with offsets and uh, different subsets of your string of ones and zeros mean different things, and you have to do sort of math to to figure it out. But that kind of stuff is already written in to a float, which stands for floating point number. So, and a double is similar to a float, except more precise. But for this tutorial, I'm mostly just going to be using floats for all my floating point needs. And this video is running long, so I'm going to sort of hand wave at doubles. They're nice. They're actually probably preferred, but they do take more memory. So anyway, if I say float gallons equals 0.5 f, and you don't have to put the f there, but it does explicitly tell the compiler that this is a floating point value. It's nice to put. You don't have to. I think you're probably supposed to, I should say. But anyway, then you can store, fraction values, or it doesn't have to be it can be 1.5, right? Or it can be 1.723, however many decimal places you want to use. Although that's where precision comes in, right? Like you'll lose some precision based on which one you're using. But these values are stored in the same bits, but in different formats. So if you had something, and that's the reason that C makes you declare your type, because if you try to store 1.5 into an int, right, and it tries to read it as an int, the ones and zeros that make up this 1.5 aren't going to come out as 1.5. They're going to come out as some integer value, because it's interpreting those ones and zeros differently, because it's a different type. And that's why C, some languages don't, but they handle it differently. But C implicitly or explicit makes you explicitly declare what type this variable is going to be of, and then ever after that, you cannot change the type of that variable. If you want that variable to be a different type, then too bad, essentially, right? So, the last one, and I'm going to go over this real fast, and hopefully I'll be able to sort of elaborate on it later, because we are going to use a lot of chars. Chars stand for characters, because so far all we've been representing are numbers, right? Oh, I spelled it wrong. Characters. So far all we've been representing are numbers, right? But what if you want to represent a grade, right? Like, what if you want to say like int grade equals A, right? Well, A is not a number, so it's not going to work, right? Uh, this will cause a compiler error for sure. But you can use the char or character, char grade, cross that out, that's bad, equals, and then if you use a single quote, right, and semicolon, that's a semicolon, not a J, then we're telling our compiler, put the character A into grade, which is a char. And chars, characters, are represented differently than numbers are, but they are represented as strings of ones and zeros as well, but they're just interpreted differently based on what type they are, right? And some programming languages also have a type called string, which is essentially a whole bunch of chars in a row. So like if I wanted to print out hello world, right? Now, C does not have an explicit string type uh, built in. It uh, it treats things like this, which we were printing out earlier, as arrays of chars. So each one of these is a separate char held in a data structure that we haven't covered yet, right? But all languages do that. C just doesn't like help you out with it, right? Which forces you to kind of know what's going on under the hood, which is a good reason to learn C first, because after you do it the hard way, then the easy way is even easier, right? So we'll deal with strings later. For now, we just have to know if we want to use a whole number, and we know for a fact it's going to always be a whole number, we can just use int. We're not going to bother too much with shorts and longs. We know what they are. If we might be needing to make decimals, right, we should call it a float. And if we want to use letters, alphanumerics, we should use char or a character. And we have to declare our things explicitly, our variables explicitly, when we declare them. We have to declare the type that they are, right? Whether it's char grade or float gallons or int cow. All right. And in the next video, I will put some of this to good use in coding examples. So stay tuned for that.